Welcome to the Walton Pie. Today we're going to be talking about how to approximate the area under a curve. So let's suppose that we have some curve and we are the area under this curve. The general idea of how we approximate this is we are going to approximate it using a bunch of rectangles. So maybe our set of rectangles looks like this. So we just say, let's break this up into a bunch of intervals, and then each interval, let's approximate the area using a rectangle. This approximation is using the midpoints. So what that means is for each of the intervals, we are looking at what's the value of the function at the midpoint, and then that's going to be the height of our rectangle. So this is one approximation of the area. Another one could be this one. This one, rather than using the midpoints, this is using the right endpoint, and then this is another approximation. This one's using the left endpoints. So what we can do is we can break up any function or any curve and break it up into a bunch of rectangles, and that is one way to approximate the area. So if you're ever asked to approximate the area using n intervals, that means take your domain and cut it up into n segments, and then for each segment find a rectangle, or in some cases a trapezoid, to approximate the area under that curve. So an approximation is going to get better if we increase the number of rectangles. So this one is using, I believe, 13 rectangles. Yes, that's correct. So this one's using 13 rectangles, but if we increase the number of rectangles, we're going to get a better approximation. So this is a much better approximation than this. Notice how much less area is missing and how much less area is overcompensated depending on if the rectangle is an overestimate or an underestimate. That amount that we are off is going to be much better than the amount that we are off here. As we increase the number of rectangles in general, the approximation is going to improve. So if we are trying to approximate the area with rectangles, we might be able to write our approximation with n rectangles as r sub n. So if we can find a way to write r sub n, meaning our approximation with n rectangles, then we could take the limit as n goes to infinity to find the area under the curve. And that's actually how we are going to define what's referred to as an integral. So it might be a little surprising, but it turns out that it doesn't matter if we approximate the curve using the right endpoint, the left endpoint, the midpoint, or just approximating it by using the value of the function anywhere inside the interval. So the limit is going to be the same regardless of which approximation is used. So since it doesn't matter which point in the interval we use, that means we can write r sub n as follows. R sub n being the approximate area, that can be written as the sum from k equals 1 to n, because we have n rectangles, of f of x sub k, where x sub k is any point inside the kth interval, and then delta x is the length of each interval. So in this image, this distance down here, that would be delta x, and then the height is going to be f of x sub k, where x sub k is some point in the interval. In this particular example, x sub k is going to be our left endpoint. And so what we can do is we can approximate this, or we can actually evaluate this sum, and that's going to give us an approximate value of the area under the curve. So that means the area under the curve will be equal to the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k times delta x. And in our next video, when we are talking about definite integrals, this is going to go much more in depth into how to compute these sums. And so that's what we are going to be doing next. If you would like to see that video, be sure to like and subscribe so that you don't miss it when it comes out. I hope you all have a great rest of your day, and good luck with the rest of your math.